Hello students, in this lecture I will give a broad outline on statistical signal processing. As you know, signal processing involves extracting information from observed data. Statistical signal processing, SSP in brief, extract this information using statistical tools. SSP works on the assumption of random signals. The assumption that the signal values at any point of time are described in terms of probabilistic models. Randomness arises because of random nature of the generation of the mechanism and limited understanding of the signal dynamics because of the uncertainties present in the signal. I will give some examples. Example 1, thermal noise. Thermal noise is typically generated as a result of the random motion of electrons in electrical conductors. It is not possible to model this signal by a deterministic process and filter out the noise using deterministic signal processing tool like a conventional linear filter. Therefore, thermal noise is usually modeled as a random signal. Example 2, a sinusoid with uncertain phase. This is the sinusoid, xt is equal to a cos omega naught t plus phi. Phi is the uncertain phase. For example, xt may represent a received carrier of a communication system. The phase uncertainty may be due to the unknown delay in the communication system. So, in this case xt will be a random signal and the randomness is because of the unknown delay in the system. Most of the physiological signals are random in nature, they are modeled as random process. For example, speech signal, this is a speech waveform, this is an ECG waveform, again we have given an EEG waveform. All these waveforms can be characterized by using statistical tools. In this example, we show a degraded image. Now, the image is a two-dimensional signal. So, it is modeled as a two-dimensional random process, also known as a random field. Different restoration methods based on SSP may be applied to deblur this image or get a clean image out of this degraded image. Statistical signal processing typically involves signal modeling by random processes, estimating the model parameters, signal estimation by optimal linear filters, power spectrum estimation and signal detection. These are the typical problems considered in a normal statistical signal processing course, but there are other topics which we will not cover. Signal modeling by a random process. Consider an observed data x0, x1 up to xn. These are the observed data. The data can be modeled by the joint probability density function PDF. This is the description. Small f is the symbol for joint probability density function. It is a function of x0, x1 up to xn minus 1 and also of parameters theta 1, theta 2 up to theta m. And in vector notation, we denote it by f x theta, where x is the data vector comprising of x0, x1 up to xn minus 1 and theta is the parameter vector comprising of theta 1, theta 2 up to theta m. So, that way we can model data by means of its joint probability density function. The data can be also modeled as a Whitesian stationary WSS random process. Such a process is characterized by second order statistics, namely the autocorrelation function defined as Rx of m is equal to E of xn into x of n plus m, where E is the expectation operator. We will discuss about this autocorrelation function in a later class. A WSS process has the frequency domain representation in terms of the power spectral density. This is a very important aspect, which is the Fourier transform of the autocorrelation function. Therefore, we can analyze the data in the frequency domain in terms of the power spectral density. Third model is a time series model. This signal is expressed in terms of a difference equation. You note a difference equation involving the signal and a sequence of uncorrelated random variables. There will be the signal and its difference, and there will be the uncorrelated random variables and their differences. The autoregressive moving average model, ARMA model, that is a popular time series model. Example, speech modeling. For the speech recognition application, the speech data are represented by an autoregressive, that is abbreviated as AR model. Here xn is a linear combination of previous values of xn. Here xn is modeled as a linear combination of previous values of xn, that is autoregression, plus some excitation term, that is g to en, where en is a sequence of uncorrelated random variables or a periodic impulse. It may be an uncorrelated random variable or an impulse, depending on the unvoiced or voiced part of the signal, because speech signal has typically it has voiced part and unvoiced part, and in the unvoiced part this en will be a uncorrelated random variable, and in the case of voice signal en is a periodic impulse. Once we have a model, we have to estimate the parameters of the model. Suppose the observed data x0, x1 up to xn minus 1 are modeled by the joint PDF, that is joint PDF is f x0, x1 up to xn minus 1 in terms of parameter theta. Parameter estimation involves finding the optimal value of theta in terms of the statistic theta hat x0, x1 up to x of n minus 1. Any function of data, this theta hat is a function of data which does not involve the unknown parameter, is known as a statistic. So, parameter estimation involves finding the optimal value of theta in terms of the statistic. Example, suppose the data is generated according to the model. This is the model, this joint PDF, it is a Gaussian PDF and it is given by this expression 1 by root over 2 pi to the power n into e to the power minus half of summation I going from 1 to n xi minus theta whole square, where theta is the unknown parameter. So, here the model is given, we have to estimate the unknown parameter theta. We can have an estimator like theta hat is equal to 1 by n summation I going from 1 to n minus 1 of xi. So, this estimator we will see how to derive this estimator. The third problem considered is signal estimation in the presence of noise. Consider the signal model yn is equal to xn plus vn. This is the observed signal, yn is the observed signal, xn is the true signal and vn is a noise. Usually it is, this noise sequence will be uncorrelated. The problem is to find the best guess for xn given the observation yn minus I going from minus m1 to m2. Here m1 and m2 may be infinity. So, how to estimate the true value of the signal from the observed noisy signal? There are two popular signal estimation problems. We will be considering the filtering problem and the prediction problem. The filtering problem is like this: we have a signal xn, it is passing through some channel and getting corrupted by noise. So, that way yn will be the modified signal plus noise, and we have to use a filter so that we can get back x hat n. So, the filtered output, this is the filtered output. The filtered output is given by this expression, x at n is summation h I y n minus I going from minus m to plus m, and this is the convolution operation. So, we can write as h n star y n, where star is the convolution operation. So, basically the filter performs the convolution operation. We have to estimate the filter coefficient h i's using some optimality criterion. That is the problem studied in Wiener filtering. Next we will consider the prediction problem. Given a sequence of observations, that is sequence of data x n minus 1, x n minus 2 up to x n minus m, what is the best prediction for x n? Now, we will be considering linear predictor x at n, which can be expressed as a linear combination of past data. So, x at n is equal to summation h I x n minus I going from 1 to m. This is again a convolution operation. The prediction coefficients are obtained using an error minimization criterion. So, like in optimal filtering, this is also a special case of optimal filtering only. So, we can apply some optimality criterion to obtain the filter predictor parameters. Linear prediction model is the heart of speech compression algorithm. So, any speech compression algorithm, for example, there is an algorithm called CELP, code excited linear prediction. So, this model is based on linear prediction of speech. Another example we will consider image restoration. In image restoration, a clean image x n1 n2 is restored from its degraded version y n1 n2. In many situations, the degradation is assumed to be linear and modeled as y n1 n2 is equal to g of n1 n2 star x of n1 n2, that is convolution of g n1 n2 and x n1 n2. This is two dimensional convolution, and the convolution operations we have already described earlier. Now, the model is like this: x n1 n2, this is the input image, it is subjected to degradation g and some noise is added. Because of that, we get y n1 n2, and by means of filtering, that is optimal filter, we should get back the original image. So, this model is used in image restoration. Example is this: suppose this is a famous image known as the cameraman image, and this is a degraded version, and if we apply some signal estimation technique like Wiener filtering, we get back this original image. Fourth problem considered is power spectrum estimation. The PSD, power spectral density, allows us to detect hidden periodic components in a signal. The convolution operation becomes multiplication in the frequency domain, resulting in easier implementation of optimal linear filters in the frequency domain. Power spectrum estimation is highly discussed area in statistical signal processing. However, in this course we will not cover this topic. This is an example. Suppose we have a sinusoid. Because of additive noise, the sinusoid is corrupted like this plot. So, now there is a noisy signal, this is the noisy signal, and we have to do the power spectral analysis to estimate the power spectrum or the sinusoid in the signal. This is estimated PSD. There are techniques available, lot of techniques are there how to estimate power spectral density, and if we plot the estimated power spectral density against frequency, we see a peak that is corresponding to the power line, that is 50 hertz. So, this is the peak and that corresponds to the 50 hertz sinusoid. Signal detection. Suppose the observed data x0, x1 up to xn minus 1 has two possible joint PDF models, that is f x0, x1 same distribution with model theta 1 or with model theta 2. We have two distribution, that is same nature of PDF, but parameter theta 1 and theta 2 are different. Detection problem involves deciding the model which describes the observed data better. So, suppose we have the observed data, now it may be because of theta 1 or theta 2, but whichever describes data better, that we will take as the model. The classical tool used for signal detection is hypothesis testing. In hypothesis testing, we make an assumption about the distribution parameter. Whether the assumption is true is tested on the basis of observed data, that is the hypothesis testing. Hypothesis testing has lot of applications in decision theory, particularly in statistical pattern recognition. The problem of classification is posed as a hypothesis testing problem by associating various pattern classes with the hypothesis. So, statistical pattern recognition is widely used in pattern classification such as species recognition, character recognition, in biomedical signal disease identification, etc. Statistical pattern recognition basically use the tools of hypothesis testing. This is one example of signal detection, detecting binary symbols 0 and 1 from the received communication data x0, x1 up to xn and minus 1, that is a frame of data, and we have two hypotheses, that is hypothesis 1, suppose this is hypothesis 1, hypothesis is generally we call it H0 and H1. On the basis of these two hypotheses, now we will interpret this data, and from analyzing this data we will say whether theta 1 is correct or theta 2 is correct. We will decide about that, and that way this is one plot which shows the distribution of, suppose this up to this instant it is 1, then up to this instant it is 0, like that. This we are identifying, we are detecting ones and zeros from this data sequence. So, this is one application of signal detection. However, we will not discuss about signal detection in this course. I will tell something about the pioneers of statistical signal processing. We can trace back to the least squares method as the origin of statistical signal processing. Least squares method is due to Adrien Marie Legendre. His no portrait of him is available except this caricature. He published the first work on least squares which minimizes the square errors, that is least square error method. So, but Carl Friedrich Gauss, who is a famous German mathematician, and he was the person who discovered normal distribution, and Gauss knew about least squares method earlier than Legendre, but he published it later on with more details. There is a big controversy about who is the inventor of this least square method, but both are credited, because any development in science or technology is because of different improvements, and both contributed to the least squares method, and that may be considered as the starting of the statistical signal processing. In middle of 20th century, there was lot of development of statistical signal processing, and particularly two group. One is American group headed by Norbert Wiener, and they worked on the optimal filtering problem. In Russia, parallelly, Andrei Kolmogorov, Kinsin, etc., many other people are there. They worked on this problem of optimal filtering problem, and also Kolmogorov is credited with the axiomatic theory of probability. Probability theory, because till Kolmogorov there was no proper definition of probability, and he gave the proper definition of probability with 3 axioms. That also we will be discussing. And Norbert Wiener is credited with the spectral representation of random signals. As I have told you that second order random process, namely the WSS processes, can be represented in terms of frequency, and that is credited to Norbert Wiener. Then many other persons are also, Kinsin for example, even Einstein knew it, and Kolmogorov also has contribution, but spectral representation of random signals is mainly attributed to Norbert Wiener. In the optimal filtering theory, there are 2 great breakthroughs, namely the Kalman filter, which is widely used, and this is due to R.D. Kalman. He is a famous electrical engineer who has contributed greatly to mathematics, and Kalman filter is used many applications including control and guidance, tracking, etc. And another breakthrough is the adaptive filter, and there is a famous algorithm called least mean square algorithm, and that is due to Bernard Woodrow and another person called Hoff. So, adaptive filter has also revolutionized the application of statistical signal processing, and learning rule of adaptive filter is also used in machine learning. In this course, we will evaluate through assignments and final examination, and all will be based on objective type questions. I will provide notes on certain selected topics, and my notes will be based on my presentations, and notes will be based on these 3 books: Hayes, Statistical Digital Signal Processing and Modeling; SMK, Fundamentals of Statistical Signal Processing, Estimation Theory. That estimation part will be covered from this book. Then Menolakis, Ingle and Kogon, Statistical and Adaptive Signal Processing. Some part of estimation and adaptive filtering will be covered from this book. Thus, we have gave a brief overview of statistical signal processing. We showed the different topics discussed under statistical signal processing. In the next class, we will give the background of statistical signal processing, that is probabilistic analysis. Thank you.